Hey there, and welcome to the Deep Dive. Have you ever paused to think about the incredible materials that make up everything from your car's braking system to the very engine of an airplane? We're talking about constant, subtle refinements, pushing the boundaries of what's possible with materials we use every single day. Today, we're taking a deep dive into some truly fascinating research. It explores how adding just a carefully chosen amount of a special ingredient can completely transform a common aluminum alloy. Transform it into a high-performance wonder material.
Indeed. And the sources you've shared, they center on a really groundbreaking research paper by T.P. Gaurashankar and colleagues. It was recently published in Fracture and Structural Integrity. Their investigation focused on Al6061, which is a widely utilized aluminum alloy, and how its mechanical and thermal characteristics are dramatically altered. Altered when reinforced with varying amounts of titanium carbide, or TiC particles.
That's a great setup. So our mission for this deep dive is to truly understand the science behind these metal matrix composites, MMCs, and uncover the surprising insights on how what seems like a subtle change in composition can lead to really dramatic improvements. We'll pay particular attention to why a specific percentage of this ceramic reinforcement appears to be a real sweet spot, kind of a magic number for peak performance, right?
Exactly, finding that optimal point.
So before we jump into the specifics of this research, what exactly are these metal matrix composites, or MMCs, and why are they such a hot topic in materials science right now?
Right. MMCs are essentially advanced materials. Think of it like this. You have a base metal, like aluminum, acting as a matrix. And that's reinforced with other materials, often ceramic particles, kind of like reinforced concrete, but on a microscopic scale.
Okay, I get the analogy.
Yeah, and the core goal is to combine the best properties of both components. So you might get the lightness and ductility of aluminum, but paired with the incredible strength and stiffness of a ceramic.
So you get the best of both worlds.
Pretty much. This means increased strength, decreased weight, lower density, and vastly improved wear resistance. All highly desirable properties in many, many technical fields. And while aluminum is a common matrix material, we also see things like copper, titanium, magnesium, and zinc being used.
Got it. And the specific aluminum we're looking at here is Al6061. Why is this particular alloy so popular in industrial applications?
Well, Al6061 is a real workhorse alloy, and for good reason. On its own, it boasts excellent inherent qualities. It's quite easy to shape and form.
Okay.
It has strong corrosion resistance, it's relatively easy to weld, and offers solid mechanical properties right out of the box. It's an ideal foundation, you could say, a great base metal to build upon when you're creating a composite.
Right. So if Al6061 is a strong foundation, what about our reinforcement material? Titanium carbide or TiC? What do ceramic particles like TiC bring to the table when you add them to an aluminum alloy?
Yes, the TiC. Well, ceramic particles such as TiC or others like silicon carbide, SiCs, or alumina, they're chosen precisely because they act as super hard fillers. They significantly boost the hardness and the overall strength of the MMCs.
Okay, hardness and strength.
Exactly. And crucially, they also enhance the tribological characteristics.
Tribological. Bit of jargon there.
Yes. It's essentially how materials behave when they're in contact and moving against each other. So think friction, lubrication, and especially wear. And TiC, in particular, has garnered significant attention in recent research for its remarkable ability to amplify these mechanical attributes.
This sounds like really cutting-edge stuff, but is the process of making these new materials incredibly complex and specialized? Or is it something more, widely accessible?
That's a great question, and it's important for understanding the practical side of things. The good news is that one of the most common and importantly cost-effective methods is called liquid metallurgy. It's also known as stir casting, and that's the method highlighted in this research.
Stir casting.
Yeah, and compared to some other advanced techniques, it's a relatively simpler process to implement, which makes it attractive for larger scale production, not just lab experiments.
Right. Scalability matters. So bringing it back to you, the listener, why should you care about this combination of Al6061 and TiC? What's the real-world impact here?
Well, just imagine the demands on components in everyday life, like disc brakes in your car, or think about high-stress parts like pistons and cylinders in heavy-duty vehicles.
Okay, yeah. High wear, high stress.
Exactly. Then consider critical parts in sectors like automotive, power generation, energy, or even aviation. These applications require materials that aren't just light and strong. They also need to be incredibly durable and able to withstand extreme conditions, often involving high temperatures and constant friction. This research directly addresses how we can develop those next-generation materials, pushing the boundaries of performance and reliability.
Okay, with those foundational concepts clear, let's now look at the experimental process itself. How did these researchers actually prepare these composite materials, and what did they first observe when they, look at them up close?
So the researchers meticulously used this stir casting process we mentioned. They started by melting precise quantities of the Al6061 alloy ingots at 850 degrees Celsius in an electric furnace.
Pretty hot.
Oh, yeah. Then, once it was molten, they stirred the liquid metal for about 10 minutes to create a fine vortex. Separately, the TiC particles, which were quite small, average size around 10 to 15 micrometers.
Tiny.
Very tiny. These were preheated to 700 degrees Celsius. And this preheating step is really crucial. It significantly improves their wettability.
Wettability, meaning how well they mix in.
Exactly. How well the ceramic particles integrate and bond with the molten aluminum. It helps prevent them from just clumping together or sinking.
Okay.
So these heated TiC particles were then gradually added to the stirring Al6061 melt, and the mixture was continuously stirred at 400 RPM by an electric motor to ensure, even dispersion.
Makes sense. Keep it all mixed up.
Precisely. Finally, the molten composite was poured into a preheated mold and allowed to solidify naturally. And they systematically created 5 different samples for comparison: pure Al6061, and then Al6061 reinforced with 3%, 6%, 9%, and 12% TiC by weight.
Okay, a nice range of concentrations. And once they had these solidified samples, what did the optical microscope reveal? What did the internal structure look like?
Well, what's fascinating here and really encouraging from a materials perspective is that their microstructure analysis showed the TiC reinforcement was remarkably uniformly distributed, evenly spread out within the aluminum matrix.
That sounds important.
Oh, absolutely critical. This uniform dispersion is key for the composite's overall properties. If the particles clump, you get weak spots. They also observed very few tiny voids or gaps, what scientists call microporosities, and importantly, no significant buildup or agglomeration of reinforcing particles, especially in those lower to mid-range concentrations.
So good mixing, few holes.
You got it. And this successful uniform distribution and strong bonding between the TiC and aluminum, that was further confirmed by another technique, Energy Dispersive Spectrometry, or EDS. It basically verified the presence of all the expected elements, indicating a well-integrated material.
Okay, so they successfully integrated these TiC particles without significant clumping or voids, especially up to a certain point. Now, the big question, how does adding TiC actually change the fundamental mechanical properties of the Al6061 alloy? Let's start with tensile strength, essentially, how much you can pull on it before it breaks.
Right. Introducing hard particles like TiCs into a softer, more ductile metal matrix significantly alters its internal mechanics, how it handles stress. When stress is applied, the load gets transferred more effectively. It goes from the flexible aluminum matrix to the much tougher and stiffer TiC reinforcement.
So the TiC takes more of the load.
Exactly. And the research showed that the tensile strength of these new composites increased by an impressive 18.47%. It's a significant jump. And this efficient load transfer, it's facilitated by chemical bonding and also mechanical interlocking at the interfaces. Where the particles meet the matrix, that's what makes the material so much stronger.
Okay, almost a fifth stronger just from this additive. That's a massive leap for design engineers. What about hardness? Its resistance to indentation or scratching.
Guess it costs. A similar story there. The presence of these hard ceramic particulates creates obstacles within the material's crystal structure. They hinder the movement of tiny imperfections called dislocations.
Dislocations, those atomic scale slips.
Precisely. They're what allow metals to deform plastically. So by impeding these dislocations, the material becomes much more resistant to plastic deformation. And that leads to a substantial increase in hardness. The study observed a remarkable 51% increase in overall hardness for the composites.
51%, that's huge.
It really is. Shows how effective these particles are at, hardening the alloy.
Okay, here's where it gets really interesting for me. They tested various percentages of TiC, right? 3, 6, 9, 12%. Was there an optimal amount for these mechanical properties, or was it just a case of more TiC is always better?
That's precisely the key finding here. And no, more wasn't always better. The research consistently showed that both tensile strength and hardness peaked at a 9 weight% TiC concentration.
9%, specifically 9.
Exactly. Beyond this point, specifically at 12 weight%, they observed a decrease in both properties. It's like finding that Goldilocks zone just right.
So why the drop-off after 9%?
Well, the reduction is attributed to a couple of factors. One is increased particle agglomeration. Basically, at higher concentrations, the particles start clumping together instead of staying nicely dispersed.
Rating weak spots again.
Exactly. And the other factor is increased brittleness. Too many hard particles can make the overall material less forgiving, more prone to cracking. This can lead to more voids and pores forming during solidification or under stress, ultimately weakening it. So yeah, too much of a good thing can in fact be detrimental.
So the very thing that makes it stronger, the particles, can also become its weakness if overdone. It's that classic Goldilocks zone effect. Fascinating. What about how the material ultimately breaks? Did adding TiC change the fundamental fracture behavior?
It absolutely did. A noticeable shift. The unreinforced Al6061 alloy typically exhibited what's called a dimpled morphology on its fractured surface. Lots of little craters.
Dimples.
Yeah, it's characteristic of ductile failure. It means the material deforms and stretches considerably before it finally breaks. It gives you some warning. However, the TiC-reinforced composites showed something different. Small, flat, cleavage facets on their fracture surfaces.
Cleavage facet sounds sharper, more brittle.
Exactly. It indicates a shift towards a more brittle fracture mode, less stretching, more snapping. This is driven by the presence of those stiff to TiC particles, and also the inherent differences in thermal expansion between the ceramic and the aluminum matrix. Creates internal stresses. And interestingly, the amount of these brittle cleavage characteristics actually increased with higher to TiC reinforcement, further emphasizing that delicate balance we talked about.
Okay, so we've established we have stronger, harder materials, but they also become a bit more brittle, especially at higher to TiC levels. How does this altered internal structure and increased hardness translate to its performance under everyday stresses, like friction and wear? That seems crucial for applications like those disc brakes we mentioned earlier.
Yes, wear resistance is another critical area where TiC reinforcement delivers really significant benefits. Those hard TiC particles, they increase the internal cohesive forces within the matrix, the van der Waals forces, and as we said, they impede dislocation movement. Both of these things together profoundly improve wear resistance.
Okay, multiple mechanisms at play.
Right. They contribute to a greater load-bearing capacity, essentially helping the material resist being scraped or ground away. In fact, they can even act as sort of micro-abrasives themselves, but in a good way. They can help form a protective layer under stress.
A protective layer, how does that work?
It's thought that under the pressure and friction of wear, some debris might mix with the TiC in the matrix to form a hard, stable layer, sometimes called a mechanically mixed layer or tribble layer. This layer then protects the bulk material underneath. The study reported a significant minimization of wear loss by about 40%.
Wow, 40% less wear. That's a huge improvement in durability for many parts. Did you get a visual confirmation of this improvement? Could they see the difference?
They certainly did. They used scanning electron microscopy, SEM, to meticulously examine the worn surfaces, and the images clearly showed that the 9% EC-reinforced composite had much smoother, more even sliding wear tracks, and noticeably less loose debris compared to the unreinforced Al6061 sample.
So cleaner wear tracks.
Exactly. The unreinforced sample showed tracks with much larger amounts of gouged-out material and debris. The SEM images really highlighted how those tight particles helped create that stable, protective surface under applied stress, significantly enhancing wear resistance.
That's an incredible multifaceted benefit. It sounds like the particles aren't just physically resisting wear, they're actively modifying the surface behavior. Given that, what stands out to you most about this particular improvement? And what happened at the higher TiC concentrations? Did the trend hold?
Well, what truly stands out is that synergy again. It's not just about adding a hard particle passively resisting wear. It's about how that particle interacts dynamically to distribute load, reduce internal friction, and even actively form a protective interface. It's quite sophisticated. And no, the trend didn't hold past 9%, just like with tensile strength and hardness.
Let me guess. Higher wear loss at 12%.
You guessed it. The research found that increasing the weight percentage of reinforcements beyond 9% actually led to higher wear loss. That persistent issue of particle agglomeration seems to be the main culprit again.
Ah, those clumps strike again.
Yeah, they create uneven load distribution, stress concentrations, and can even get pulled out, making the material more prone to wear. It just unequivocally underscores the importance of finding that optimal balance. 9% was key.
Okay, this 9% figure is becoming really central. Strength, hardness, wear resistance. All peak there. Now, beyond mechanical stresses, many high-performance applications involve significant heat. How do these TiC-reinforced composites behave when things get hot? Let's first talk about thermal conductivity. How efficiently do they transfer heat?
Right, thermal conductivity is vital. Think about dissipating heat away from, say, engine components or electronics. The study found an interesting trend here, too. The thermal conductivity of the Al6061 composites progressively increases with temperature, which you might expect. But importantly, it also increases with the Tilly weight proportion, but only up to
9%.
You're catching on. Up to 9 weight% TiC-Co.
Okay, so better heat transfer up to that point. And what were the numbers for this increase? How much better did it get?
The maximum thermal conductivity measured for the Al6061 plus 9W2% TiC-Co composite was 194.0256 watts per meter degree Celsius, which is significantly higher than the base Al6061 material, which was around 166.9845 millimeter degree C.
That's a decent jump. Better heat dissipation.
Definitely. Suggests improved performance in heat-sensitive applications. However, similar to the mechanical properties we discussed, at 12 weight% TiC-Co, the thermal conductivity actually decreased again.
Okay, that pattern is really consistent. Why the drop in heat conductivity? Same reason, agglomeration.
It seems likely, yes. The reduction is again linked to the agglomeration of those ceramic particles. You can imagine these clumps hindering effective heat transfer. They might essentially shield the aluminum alloy matrix locally, creating barriers to smooth heat flow through the material, almost like tiny insulating pockets, as you suggested earlier.
Fascinating how that one microstructural issue, clumping, affects so many different properties. Okay, so conductivity peaks at 9%. Now, what about thermal expansion? How much a material expands or contracts with temperature changes? That's incredibly important for dimensional stability, right?
Absolutely. The coefficient of thermal expansion, or CTE, is a crucial characteristic for any material, but especially for composites, particularly when they operate under varying thermal loads, like in engines cycling on and off. Mismatched expansion can cause huge stresses.
So what did the research find about CTE?
It demonstrated a very favorable trend. The thermal expansion coefficient decreased for Al6061, as well as its composites containing TiC. Decrease as both the operating temperature increased and as the TiC concentration increased.
So it became more thermally stable as you added TiC. That's critical for reliability, surely. Does this mean these composites are less prone to issues like thermal fatigue, where repeated expansion and contraction can cause failure over time?
Exactly. That's the implication. Maintaining dimensional stability under thermal loads is paramount in engineering design. Materials that expand less, or at least more predictably, avoid generating those damaging internal microstresses, which is vital in applications where precision is key. Think jet engines, precision instruments, even electronics mounting.
So how much did the CTE drop? And did it follow the 9% rule?
It did follow the pattern. The thermal expansion coefficient steadily dropped as the amount of reinforcing material increased, reaching its lowest value at that familiar 9 weight% TiC-I. At this optimal point, the CTE was measured as Brenno 0.199 a 10⁴ per degree Celsius. Compare that to the base Al6061 alloy's highest CTE, which was 0.249 at 10 Ti. A substantial improvement in stability.
Okay, a significant reduction.
Yeah.
But let me guess what happened to 12% TiC for CTE. Did that trend reverse again?
You're absolutely right. We see that familiar turnaround. The CTE value started to increase again when the TiC content went up to 12 weight%.
High this time. Still agglomeration?
Agglomeration likely plays a role again, yes. The paper suggests factors like increased surface roughness at higher TiC content could lead to higher internal friction. And the TiC particles themselves might act as abrasives internally at these high concentrations, increasing friction and wear within the material structure, which contributes to more expansion. Micrographic research also suggested that reinforcing aggregation and clustering became more prominent along with that increased CTE value. So it all points back to too much TiC causing structural issues.
It's remarkable how consistent that finding is across mechanical and thermal properties.
Mm-hmm.
So what does this all mean for us? Let's tie it all together. Across the board, strength, hardness, wear resistance, thermal conductivity, thermal stability, there's this clear, consistent sweet spot.
That's absolutely right. The research unequivocally highlights that a 9 weight% concentration of TiC particles in Al6061 MMCs delivers the most significant simultaneous improvements across all the measured properties. Just to recap the peaks at 9%, tensile strength saw an 18.47% increase.
Impressive.
Hardness jumped by 51%.
Huge jump.
Wear resistance improved significantly with a 40% reduction in wear loss.
Very durable.
Thermal conductivity reached its maximum of 194.0256 millimeter degrees.
Good for heat dissipation.
And it achieved the lowest coefficient of thermal expansion, 0.199 dies 10 TeF, meaning maximum thermal stability.
It really is a compelling demonstration of material optimization at the micro level.
It truly is.
It's also a testament to precise material engineering, isn't it? Just a few percentage points make the difference between a good material and a truly exceptional one for these demanding applications. So, given this precise threshold, does it open doors for more predictive modeling and materials design? Could we start to engineer for an optimal percentage from the outset, rather than relying so heavily on trial and error testing?
That's an excellent point, and yes, absolutely. This kind of precise, consistent finding at 9% is exactly what helps validate and refine those predictive computational models. It shows that while adding reinforcement generally improves properties, that's the basic idea, there's a critical balance point. Too much, as we saw, leads to negative effects like particle agglomeration, increased brittleness, poor heat transfer.
Which can negate the benefits or even degrade performance below the starting point sometimes.
Exactly. Understanding these precise thresholds and the underlying physical mechanisms behind them, the why behind the 9%, is what truly drives innovation in material science. It moves us closer to designing materials with highly targeted properties, almost from first principles computationally, before we even mix things in the lab.
A powerful concept. And that's our deep dive into the fascinating world of Al6061 and TiC composites. We've seen how a common everyday aluminum alloy can be transformed into a high-performance material simply by adding a carefully calculated amount of ceramic reinforcement, just a pinch, relatively speaking. And the precise distribution of those particles, finding that optimal balance like the 9% TiC we focused on today, is absolutely critical. Critical to unlocking new possibilities for engineering and technology. Thank you for joining us on this exploration. So next time you hear about a new material breakthrough, maybe consider the subtle dance of percentages and microstructures that allows it to perform its magic. This 9% sweet spot isn't just a random number. It's really a testament to how profoundly specific material science has become, guiding us to engineer solutions almost atom by atom. So the thought to leave you with is, how might other seemingly small adjustments in composition, perhaps in different materials, unlock entirely new possibilities for the world around us? What other magic numbers are out there waiting to be discovered?